So good morning, welcome to Krishna's classroom. This lecture we start on a new stage. So far we had been looking at the structure of the inner product spaces, especially finite dimensional inner product space. Occasionally we had been digressing into infinite dimensional spaces also. But the focus had been on finite dimensional inner product spaces. This is actually preparing the ground, because our actual program is to consider mappings on inner product spaces. Okay, so we start with this activity now, beginning with what are called linear functionals. Now we are already familiar with linear functionals. Okay, so we have x is an finite dimensional we assume over depending on which it will be a real space or a complex space. What you call unitary space or the Euclidean space. Now we first look at what a linear functional is. A linear functional is a map from denotes the inner product. So we are now interested in considering mappings from linear mappings x to C or R depending on the space. So what's a linear map? A linear map is the following. Okay, we'll use a different notation later, but to begin with, so phi is a map from x to C or R. Phi of alpha 1 plus alpha 2 is equal to alpha 1 times that is linearity. So here x1, x2 this is what you call a linear map. And we have extensively looked at linear maps from vector spaces to the associated field. So here C is a one-dimensional vector space and X is finite dimensional. I don't know whether we made any assumption about that. Let dimension of X take this to be n dimension, so that it's finite dimensional and it's of dimension n. Now we connect the linear functional with the inner product. Okay. So that's what we want to do. So define where y is a and of course for x belonging to x. This is the definition. Then we observe that this is a complex number or a real number. Therefore, psi is a map from R and psi is linear. That's easy to see. It's linear in the first argument and conjugate linear in the second argument. We are keeping y fixed, therefore psi is associated with the vector phi, or psi is induced by the vector y through the inner product. Vector y in fact further every vector induces a linear functional on x through the inner product. So what we have is every vector induces a linear functional on the inner product space through x. Because many of these statements are true for infinite dimensional spaces with some caution, but we will stick to finite dimensional spaces as far as this discussion goes. So now what we ask is the following: is the class all linear? Larger than the set of vectors on This is the question that you are asking. Because we have seen that every vector induces a linear functional. Therefore, you can associate a vector with a linear functional. So, it is something like this. So, this is the, let me use the notation x prime is the set of all linear functionals. What we have seen is that x is embedded in x prime. Okay. So, y belonging to x induces a element of x prime. What I am asking is this: are these identical? That means the only linear functionals on x are those induced by the vectors in x. Okay. So, our objective is to prove this theorem. So, let us investigate. Okay. Now, one side is clear that y induces a inner product. Now, we will use the notation. So, let x prime then x prime is a vector space. C or R, and what we have is this psi 1 of so it is a linear functional and alpha belongs to so it is a linear space. Now, you see that sum of linear functionals is a linear functional, scalar multiple of a linear functional is a linear functional. Okay. This is quite easy to verify. Okay. But we do not know anything more about the structure of that. In fact, you recall when we considered these problems earlier, we did not have any further structure on x or x prime. But now, x is also endowed with what you call an inner product, which in turn induces a norm, which in turn induces a metric. Therefore, x is a metric space. So, there is rich in structure. Okay, right? And as a linear space, you can introduce x prime. Right? And we shall ask questions like, can you have these structures in a natural way induced so that x prime also becomes a space with a possibly an inner product? That is the question. That means that is every linear functional is induced by through inner product. This is the question that you are trying to resolve. If you have resolved that, if yes, is it possible to an inner product on X prime in a natural? These are the questions that we are going to explore. Okay, so let us start with begin with the analysis, right? So we shall use y prime to denote a typical vector of rotation That's the notation. Okay, what next? So we in fact show that the answer to this question is yes. Okay, so this is expressed in this theorem. In the general scenario, namely Hilbert spaces, this result goes by the name Riesz representation theorem. That is why I have put Riesz representation theorem in the title, although we are only working on a very restricted class of linear spaces. Okay, so we shall make the statement: for any linear functional y prime, not y derivative, it is y prime on a finite dimensional inner product space X there exists a unique vector such that y prime of x equal to inner product of x with y belonging to and this is uniquely determined. So once y prime is given, there is a vector x here, I mean in the y in the vector space x, so that y derivative of x is x, the inner product of x with y. That means if this is x and this is x prime, then given a y prime, there exists a particular y in x such that y prime of x so that they are connected by this. Y prime is an element of x prime, it's a dual space of x. Okay, right. But they are more intimately connected in terms of further involvement of this particular inner product structure. Right now, I have not said anything about x prime. X prime is just a linear space of all linear functionals on x. Had I been talking about the infinite dimensional spaces with a certain norm with x, an inner product space which is infinite dimensional, I would have been restricting myself to the so-called bounded linear functionals or continuous linear functionals after introducing all the necessary notations on this. Okay, so if you take bounded linear functionals on x, then you can make it a normed linear space by defining a norm using the norm on x. So all this is possible. So we will not go into it, but all those things are assured here because we are working with the finite dimensional vector spaces. So the dimension of x is n, so also the dimension of x prime. They are finite dimensional vector spaces. Okay, and then you can introduce a suitable norm here or even an inner product, or so that this becomes a metric space, and this becomes what is called a y prime can be considered as a of course that doesn't need that, but y prime is a map from x to c. Once x has an inner product, it is a metric space. So you are talking about y prime is a map from the inner product space x to C or R, and both have topologies. Therefore, you can talk about y prime, and you see that if x is finite dimensional, implies y prime is bounded or continuous. Synonymous, which is the same as continuity. So all these things are there that we will try to explore. So essentially we are working on what are called continuous linear functionals, and this aspect will have to be specifically mentioned the moment you go to infinite dimensional spaces, where you may encounter unbounded or linear functionals on the inner product space or the normally linear spaces. So that's all. For the time being, we shall not bother about it. So we are now working on finite dimensional spaces. So let us try to prove this theorem. So if y prime equal to 0, what does it mean? Y prime of x equal to 0 for every, this is the meaning of that. Then we choose equal to 0 vector, so that y prime of x with y equal to 0 is valid. Now our task is for any y prime in x prime, we want to identify the corresponding y so that this relation is satisfied. So now we assume y prime is not equal to 0. What does it mean? This means y prime of x is not identically zero. It may be 0 for some elements, but not identically 0. Okay. So let us define. So let M be defined as the subspace, the set of all x belonging to x for which y prime of x equal to 0. Okay. So M is a and because of the assumption that y prime is not equal to 0, dimension of M equal to some small m which is strictly less than n. Therefore, as we have using the previous result, we can talk about what is called M perp. Then of course we know that x is equal to this is the decomposition theorem that we did last time. Okay. Now we want to somehow craft a particular y which serves our purpose given y prime. How to do that? So given y prime not equal to 0, we identified a y belonging to x so that the inner product, that y prime is represented through the inner product. So that's our task. Okay. Such that now, you see, n is not equal to 0, okay, which implies there exists a vector y naught. So let me denote this by z naught belonging to n such that z naught is not equal to 0 and such that what we do is, so z naught is a non-zero vector, therefore define divided by norm of z naught okay, so that norm of y naught is equal to 1. So we now work with z naught, we forget about this z naught and then start working with y naught, okay, right. So we define a vector the complex conjugate of y prime y naught multiplied by y naught. Now we take the complex conjugation here because later things will be clear why we need this kind of a choice. This happens when the associated field is C. If it is R, then of course this is a real number, therefore this conjugation does not matter. So let me just mark this. This is the crucial definition. Okay, then we make some observations. Let us compute let us write xy, then inner product of x with y is y prime y naught x y naught. Therefore, for y equal to y naught, we see that we have so our choice is apt for the vector y equal to y naught, and for all x belonging to M, inner product of x with y okay, how did we choose y naught? Y naught is in M pair. So x in M and y belonging to, see, y belongs to M pair, xy equal to 0, but this is true. Why? Because you have xy equal to and this is equal to 0. That's the reason. Because you have y naught belonging to M pair. Therefore, for every x belonging to M and for x equal to y naught, this is true. That is, you have That is true. So now what we do is we start with an arbitrary vector. So let x belonging to x. Define, so what we do is we define x naught in the following. We define, let x naught be defined as where lambda equal to so for each x we are defining this way. Okay. Then y derivative at x naught equal to, because it is linear, and they are non-zero, therefore this is equal to hence y derivative of x is equal to y derivative x naught plus lambda times y derivative y naught, where lambda is as given. That is, x is a linear combination of x is a linear combination of x naught and y naught. Where x naught is of course a vector in, see this, what does this say? This says that this says that is a vector in and a scalar multiple of so each x can be split in this form. So each x can be written as x naught plus and you see that this is an orthogonal combination where x naught belongs to that is a vector in M and a vector in N. Therefore, this is a sort of unique decomposition that you have. Okay. Now let us work on this. Because you have x is equal to m plus m per and m intersection m per has only 0 vector, and we have already obtained the resolution of x in terms of a vector in M and a scalar multiple of y naught. Now, see, we use the consequence of this. We know that y dash of x, see, y dash of x naught equal to 0 x okay. X y for every x in M and for y naught. Now this we have proved. Consequently, what happens here? So y dash of x, this is equal to y dash of x naught plus which is equal to therefore what do you have? This is equal to x naught y plus and that's equal to inner product of x with y. So for an arbitrary x belonging to x, this is true. So we have proved the representation theorem. This except for uniqueness. Now we prove that this is unique. This the choice of how do you do that? Let y2, which implies inner product of x y1 minus y2 equal to 0. This is true for every x. That is, we have and in particular when we have norm of equal to 0. What does it mean? y1 equal to y2. Thus, the choice of y is unique. This is what we have proved. That completes the proof of the theorem. Okay. Now we look at further aspects of this. See, one thing I said in the beginning is that on X you have an inner product structure. What about Y prime? So you see that clearly there exists a x prime. That is, the connection is this. Connects and vice versa. So you have So it's a one-to-one onto map. Now we ask the following question: is this map? So let us define. So let phi, that is phi is from, that is phi of y, that's a map. For any y prime, there is a y in x. For any y, there is a corresponding y prime, where of course this is how it is defined. This is the connection. So that's how phi is defined. Okay. What we have seen is that this is a one-to-one onto map. For that we observe the following. We observe that phi prime, okay, y prime of x equal to which is equal to alpha times y prime of x. That is true. However, alpha y prime, this is equal to alpha y, and this is equal to alpha conjugate, which is equal to alpha conjugate y prime of x. Okay, so this is the problem. See, that is alpha y prime is associated with alpha conjugate y. Okay, now you can easily see that suppose y1 is associated with y1 prime is associated with y1, y2 prime is associated with y2, then this is easily done. Okay. However, alpha y prime is associated with alpha conjugate y prime. Yeah, so this is associated with alpha conjugate y prime. Okay, because what is the reason? The reason is that alpha y prime of x equal to alpha conjugate. This is the reason. So it is not, this is not linear, okay, right? So y1 plus y2 gets mapped to y1 prime plus y2 prime. That relation is okay, but it is alpha y is not mapped to alpha y prime. Okay. In fact, what happens is it is mapped to the conjugate of that. So alpha y is mapped to alpha conjugate of y prime. That's the problem. So it's a conjugate linear map. So the linear, so the linear space structure is not carried as such under this map of associating y prime with y between x and x prime. Okay, so the linear space structure is not carried as it is. It is actually the conjugate linear. Okay. So we have the okay, so that is an observation. So this is not a linear isomorphism. So consequence is that what we have discussed is not a linear isomorphism. the linear structure is not preserved. Preserved. That's the problem. However, it is conjugated. This may be called conjugate linear isomorphism. So x and x prime are not as such isomorphic to one another. They are conjugately isomorphic. The reason is this: x and y, x and x prime because of this conjugation that comes up. Now let us ask the question, however, is it possible to define an inner product in x prime? Prime using the inner product in that's the question. So our instinctive choice is however, you can immediately see this. Okay. You have alpha y1 prime, y2 prime. This is equal to, see, alpha y1 y2, which is equal to alpha conjugate y2. Okay. So this is not in the format in which this should work, because if it is an inner product, this we would like to have alpha y1 prime y2 prime to be equal to alpha y1 prime y2 prime. So that is not true. So there is a conjugation coming there, but it can be easily remedied. So what we do is, so this is not the right choice. Something wrong with it. Okay. So what do we do? However, if we define modified by as then it works. Why it works? Because then this is equal to y2 alpha bar y1 which is equal to alpha y2 y1 so that problem has been rectified here by this choice. Therefore, this is the correct choice for the inner product. Now one can easily verify that this is an inner product. It is linear in the first variable and conjugate linear in the second variable. Now we verify these things, that is clearly belongs to C. And this is equal to 0 0. Now this is linear in the first variable and conjugate linear. in the second. And clearly, okay, so nothing to be. It is conjugate symmetry. So that proves everything. Okay, therefore this is an inner product. Therefore x prime with and you call this star. So they are not isomorphic to one another, but conjugate isomorphic to one another. Now this is the connection, and this representation of the inner product by a vector, or sorry, the linear function by a vector, is called the Riesz representation. Okay, so thank you very much.